Hello, viewers. You're welcome to Educational World Selaxi. This is the WAEC 2024 Physics Practical video on electricity. I know out there has been so many videos talking about physics practicals with so many people performing the experiment, but I am here to show you the one and only way by which you could outsmart this WAEC practical and think like the examiner. So this particular video is for the smart people. So I call this the Physics Practical Cheat on Electricity 2024. So I am going to show you exactly how you are going to tackle this problem without even touching the apparatus. This is what I'm going to do. So let's dive right in. You already know that WAEC asked us to provide this set of apparatus. I'm not going to go through them because I know you know them. So these are the set of apparatus that the WAEC said we should provide. Here they are. Okay. So, and the question is going to be as thus. So you are provided with two wires marked P and Q, a resistor marked RS. That resistor is going to be 1 ohm resistor and other necessary apparatus. So we are going to connect the circuit as shown in the diagram. So we are going to connect it as shown in this diagram. All right. So we are going to connect the RX, the 1 ohm resistor, at the left hand side gap of the meter bridge, and the wire P. We'll first of all use wire P for this experiment. Okay. Then wire P, we'll first of all connect it at the right hand side of the meter bridge. And once we've done that, we first of all take the length of wire P to be 100 and then find the balance point of the center zero galvanometer on the meter rule on the meter bridge. Okay. And once we've done that, we evaluate for LX and LP for wire P. All right. And we will repeat the experiment for other procedures of L with L 90, 80, 70, and 60 respectively. All right. Once you've done that, we will take away wire P and replace it with wire Q and repeat the same procedure as we've done previously. Okay. So we will still get the corresponding values of LX in this case and LQ in this case now. All right. So once we've done that, we will evaluate for R1 and R2 as the case may be and plot the graph of R2 on the vertical axis and R1 on the horizontal axis. We'll find the slope, okay, and evaluate for K, which is the square root of the slope. So that is that. So now, for us to be able to outsmart this practical, okay, we will first of all need to perform or get the first value of this experiment. So one of my friends, Vindal's Academy, okay, I got the first values from his experiment. I also put it in the description down below for you to find and watch his video if you want to. But that is where I got the readings for my first values in this experiment. Okay. And it's going to be helpful for us. Okay. Now, I want you to remember that this experiment is not the WAEC physics question, but is probably the most likely question. And this is the way you're going to outsmart it. So I want you to learn the tricks. Okay. Learn the tricks. So no matter the values they may change, so these tricks will still work. Before we proceed, I would like you to hit that like button and the subscribe button and the bell icon for notifications when I upload more videos. All right. So let's go on. So we are going to use wire P. So using wire P, and these are the values of the first experiment derived from my friend Vindal's concepts. All right. So when he performed the experiment using wire P, here he used the length 90. So he skipped 100, although the experiment said we should start with 100. So for the case of this video, I'm going to start with 90 because that is what he started with. Okay, so when the length of wire P is 90, length LX was gotten as 73.0 centimeters. Okay, and the length LP was gotten as 27.0 centimeters. All right, and evaluating for R1 based on what the question said, R1 was what? 0.37 ohms. We can evaluate for R1 using the relationship R1 is equal to LP over LX multiplied by RX. All right, so when we do that, that is how we got that our R1 is 0.37 ohms. Don't forget about your units. It's very, very important. Yes, there is so much calculation in this video, yeah, unlike the other ones, but once you've gotten a hold of it, believe me, it's very, very easy. You will say, I said so. All right. Now, there is always a relationship between the resistance of a wire and its length. Very, very important. That is the principle where this practical is hinged. So we can find this relationship in this formula. So the resistance of a wire is directly proportional to its length and inversely proportional to its area. So this constant here is called the resistivity. This constant here is called the resistivity. So we will not go about all the theories and everything. So let's go ahead. So where R is the resistance, P and A are constant. So the resistivity and the area are constants. So what is changing here is the length of the wire. So once the length of the wire changes, the resistance of the wire will change as well. So the more the length, the more the resistance. Okay, where K is equal to resistivity all over the area. Very, very important. Okay, so let's go ahead. So to find K is going to be the resistance all over the length. Okay, so now in this case we're going to consider the wires P and Q as resistors in this scenario, with their resistance varying according to their length. So to clarify this concept, I'm going to introduce some new variables. Okay, now here I'm going to introduce RP. RP will be the resistance of wire P at any given length, because we are going to start with RP. Okay, we are going to start with wire P. That is why I'm saying RP is going to be the resistance of wire P at any given length. Okay, all right. So we know the relationship that says that the resistance is equal to KL. Don't forget that, very important. So therefore, we can say that the resistance of wire P will be equal to the constant of wire P multiplied by its length at any given time. So now this is very important. You know that on a normal day, WAEC, they are very, very clever. On a normal day, they should have used a resistance box here to fix in this position for the length of for this place this wire is positioned. They remove the resistance box in this case and introduce a wire of length, of a given length, that you will be varying the length to provide varying degrees of resistance, just the way the resistance box will do. This is very important. So if you've gotten hold of that in your head, let's carry on. So there is a relationship of a potentiometer that says since this is the balance point, okay? So the ratio between the resistance here and the length here is equal to the ratio between the resistance of this wire here and the length here, because they are at equal potential. The potential at the two sides are equal. So that is why I said Rx over Lx, Rs over Lx is equal to Rp, the resistance of the wire P, the length of wire P divided by the Lp. Very important. So this ratio will give us a constant. From A to C is 100. Okay, so if A to B is Lx, so B to C can be said to be 100 minus Lx. That's what I said here. So I can say, but LP is equal to 100 minus LX. Therefore, I can represent this relationship here as this. I can represent this relationship as this. We can now go ahead and find LP by simply subtracting LX from 100. It's as simple as that. All right. For wire P, all right, when the length is 90, just like my guy performed the experiment, okay, we need to find the resistance of that length. We need to find the resistance of that length. What is the resistance? What is the resistance of this wire when its length is 90? That is what I'm trying to derive. So how do we do that? So based on what we've gotten previously, based on our table of values previously, so I'll use this relationship. Rx over Lx is equal to Rp, which is the resistance of this length of wire P when its length is 90, divided by Lp. So Rx is 1 ohm. That is what you're seeing here. 1 ohm divided by, from our values, what we've got Lx as 70.3. So it's equal to Rp, which is the resistance of wire P when its length is 90, is unknown for now, divided by Lp, which is 27. And once we substitute everything together, we will now have that our Rp is going to give us 27 over 73, which is equal to 0.37 ohms. The resistance of wire P at that length is equal to Kp, which is a constant. This Kp is a constant multiplied by the length L. So that is what I need to find now. Okay? So using this relationship now, so Kp is going to be the resistance of wire P at 90 at 90 cm, which is 0.37, divided by that length 90, which gives me 0.0042 ohm per cm. So when we reduce the length to 80, the first thing we have to do is to find the resistance. Find the resistance of the wire P when its length is 80. So we need to find this resistance. When we find the resistance, everything is easy. We can now use our ratio. Do Rx over Lx is equal to that resistance we found over Lp. As easy as that. Rp is equal to Kp multiplied by L. Okay, and the Kp is a constant that we'll be using throughout the experiment, which is what, 0.0042 ohm per cm. So we are going to multiply this value with the new length 80. And when we multiply this value with the new length 80, we are going to get that Rp is going to be 0.336 ohms. Very important. All right. Since we've gotten that it is 0.336 ohms, what we will now do, we will now use the relationship of potentiometer to determine what Lx and Lp. And what will that be? So it's not going to be Lx over Lp is equal to Rp all over 100 minus Ls. Remember, 100 minus Ls is the same thing as what? Lp. So we will substitute the values where necessary. 1 over Ls is equal to 0.336 divided by 100 minus Lx. And when we go ahead to solve it, x, we are going to have that Lx here is going to give me 74.9 centimeters. Ls is 74.9 centimeters. And when we subtract 100 from 74.9 centimeters, we'll have 75.1 cm. So these are the new values for Lx and Lp. This, as the case is. Okay, so now we'll now go ahead and put in our values in our table. Length is 80 cm for wire P. Lx is 74.9. Lp is 25.1, and R1 is 0.34. R1 is 0.34. So how do we evaluate for our R1? So R1 is Lp over Lx is time multiplied by Rx, and everything, when we simplify it, is going to give us 0.34 approximately. It's an approximation, okay? This is the same with this. They are the same. They are the same. it's just something that got to my attention. When I was doing this, I didn't notice that in the first time, okay? So I just got to notice it not too long ago. So let's go ahead. Now, the same thing goes ahead. So when the new length is now 70, the same principle applies. So I'm going to be fast this time around because of time, okay? So the same thing happens. So RP is equals to KPL. And when we find the resistance of, so we have to find the resistance of wire L and when the length is 70. And when we do that, we are going to have, let's just go ahead, okay? So we are going to have that the resistance is going to be 0.294 ohms. Okay, so with the same relationship of potentiometer, now we're going to find the value of Lx and Lp. So doing that, we are going to get, okay, that Lx in this case is what, 77.3, and Lp in this case is going to be 100 minus 77.3, which is going to be 22.7. And when we put all that in our table of values here, we now have that the new table of values is going to be, when it's 70, LS is 77.3, this is 22.7, and this other one is 0.29. Okay, just like I have told you, if you watch closely, you will see that, and these are the same. This is the same thing with this. They are the same. They are the same. Just an approximation. All right. I just noticed that. Okay, when the length is 60, the same thing happens. We'll find the resistance of wire P at that length, 60. Okay, so it's very simple. We know the value of our Kp, the constant Kp, which is 0.0043. Okay, so substitute it in here. So it's 0.0042. Okay, so when we substitute it here, and we'll find the resistance of wire L at that length, 60. Okay, so 0.0042 multiplied by 60, we will have 0.252 ohms. 0.252 ohms. So that's that. So we'll go ahead using the relationship of the potentiometer, okay, in this case, and substitute the values where necessary. The value of Lx is going to give us 79.9 centimeters. So the LP in this case will be 100 minus 79.9 centimeters, which is going to give us 20.1 centimeters. Very interesting, isn't it? You see, once we've gotten hold of the secret, it's very easy. We can just go ahead now and just crack on. Don't forget to hit the like button, the subscribe button, and your bell icon for more of my videos. Believe me, I am back. I was out for some time due to my studies in the UK, but now I am back. I am back for you guys. So, all right, let's go ahead. So when we now substitute everything in our table of values, we are going to have that. So we are going to have in this case that when L is 60, this is 79.9, this is that, and R1 is 0.25, okay? That's similar here. This value here is similar to this value here. Very important. Very similar. Okay. So that is for wire P. That is for wire P. So now let's go straight to wire Q. So the same principle happens when this is wire Q. When this is wire Q now, this will become LQ. This is still LX. This is still 1 ohm. All right. So the same principle that happened with wire P happens with wire Q. All right. So let's go ahead now. So I'll just talk briefly about that. So the RQ in this case is the resistance of wire Q at any given length L. All right. So this is the relationship R is equals to KL is very important. I have said that several times. So therefore, we can see that RQ is equals to KQL. So we're going to use the relationship here. Rx over Ls is equals to RQ over. RQ is the resistance of this wire here. So that's my RQ. So RQ over LQ. Very important. All right. So let's go ahead. Because we'll be having two unknowns, Lx and LQ, I have to represent LQ in terms of Lx. So representing LQ in terms of Lx will make it easier for us. Okay, so that's what I just did here. That's it. All right. Now, going ahead, we now have that you see using wire Q now. So my friend Vindal's Academy, he performed the first experiment again using LQ when the length is 90 centimeters. He got LX to be 71.8 and LQ to be 28.2. And evaluating for R2, we've got that R2 here is 28.2 divided by 71.8 times 1, which is 0.39. So that is that. So I just took it from his experiment, okay, to teach us this. Very important. So let's go ahead. Now, for wire Q, okay, when the length is 90, we need to find that constant. We need to find a constant, okay, of wire Q. We need to find a constant of wire Q. Very, very important. So from the result that we've got from the first experiment, we just substitute it. So Rx over Ls is equal to Rq over 100 minus Lx. So we got Rq as, okay, 0.39 ohms, right? So, but we have a relationship we need here. We need this relationship to get the value of KQ. So KQ in this case is going to be the value, what we got from RQ divided by 90, which is 0.00433, similar to what we had earlier, which is 0.0042. Okay, so this KQ is a constant for wire Q at any given length. It's a constant for wire Q at any given length. Okay, length is 80. What happens now? We'll first of all find the resistance of wire Q at the length 80. Okay, so see the same thing. We just have to multiply KQ with the length, and when we do that, okay, we will have that KQ is equal to 0.00433 multiplied. So RQ is going to be 0.00433 multiplied by 80. KQ is that value, it's a constant. KQ is this value here, it's a constant, and we are going to use it throughout the experiment. So when we multiply that, we'll find out that the new value of our RQ is going to be 0.0346. Very important. So using the potentiometer relationship, okay, we'll find Lx and Lq. So when we do that, we are going to have Rx is equal to Rx over Lx is equal to Rq divided by 100 minus Lx. And when we substitute everything where necessary, we are going to have here that Lx is going to give us 74.3. If Ls is 74.3, LQ is very easy. So 100 minus 74.3 will give us 25.7. So we are going to put that in our table of values. I'm putting that in our table of values. So we now have that when L is 80, Lx is 74.3, LQ is 25.7. And if we're looking for R2, we have R2 as what, 0.35. So it's as easy as that, 0.35. Just like I have said, this 0.35 is an approximate. So you can see that it's still the same thing with this. It's the same with this. It's the same with this. Okay. So solving to get the value of the resistance when the length is 70, and that was 0.3031. So using the potentiometer relationship, we want to find the value of Lx and Lq. So in this case, we have that Lx is going to give us 76.7 centimeters, and LQ, sorry, this is supposed to be LQ. LQ is going to give us what, 23.3 centimeters. Okay, when this is 70, this is 76.7, this is 23.3, and this is 0.3 ohms. Okay, so, and this is the evaluation for R2, how we got it. So let's continue. The same thing goes to when it is 60. So when it is 60, when the length is 60, we still go through the same procedures, we find the value of the resistance when the length is 60, and we use the potentiometer relationship to get the values of Lx and Lq as the case may be. All right, Lx is 79.4 and Lq is 20.6 centimeters. So we now go ahead and put it in our table of values. So going ahead in our table of values now, we now have that When this is 60, this is 79.4, this is 20.6, and this is 0.26. All right. So that is that. Okay. So now we are going to look at this is how we got the R2 valuation. Okay. So now we are going to look at our composite table, because the question asks us to plot the graph of R2 against R1. So I just put up a table, R1 and R2. So we are going to plot the graphs of R2 versus R1 in the next video. So thanks for watching, and thanks for staying with me to this moment. So we'll be looking forward to our graph plotting in the next video. Thank you.